Inference is the process of reaching conclusions from evidence. But what do we mean by evidence? Well, if we look around this office, we see a mess of papers, a stack of journals, a computer, some library books that I should have returned by now, and on the back wall, I've got my class notes and some other notices. Now, you can infer from all this evidence that I'm a college professor, but in the case of statistical inference, the evidence has to be numerical. Now, such informal inference is as common in statistics as it is in any other areas of our lives. But formal statistical inference requires that we make probability calculations in order to determine how confident we can be about our conclusions. Now, one of the most intriguing aspects of statistical inference is the fact that chance, which usually enters into our lives to mess things up, is the ally rather than the enemy of confident conclusions. At first glance, the opposite seems true. Suppose that the Gallup poll, for instance, decided to take its weekly public opinion survey twice, separately and simultaneously, selecting two random samples, sending out interviewers, and asking the same questions.
At night, I don't think that as a woman I'm safe, completely safe anywhere that I walk, even in areas that would be called safe. I always feel that I have to be on my lookout. I always feel that it's important to
we have some
be aware
house
of
breaks,
my
but no more or less than anywhere else. So it's really not a fear. It's something that happens. Fortunately, nobody's been hurt by it. People lose some things.
It's a little boring. I think it's more fun to live in the city, and it's a little bit more alive.
I'm not worried about crime in my neighborhood. It's a family sort of neighborhood, and
Two random samples, each selecting 1,500 of the 165 million U.S. residents age 18 and over, will of course contain different people. And those different people will of course hold somewhat different opinions. So Gallup's announcement that 45% of Americans are afraid to go out at night for fear of crime actually refers to the 1,555 particular people in one particular sample. Indeed, if Gallup had taken a simultaneous second survey, no doubt the results would have been different. And the same could be said for any survey, like the unemployment rate, and for the same reason. Random sampling may eliminate bias, but as we've seen earlier, it can't eliminate variability. So how can we trust the results of a random sample, knowing that a second sample may very well yield a second result? How, for that matter, can we trust the results of an experiment? Take the Physician's Health Study, which is testing the effects of aspirin and beta-carotene on reducing heart disease and cancer. The PHS has recruited 22,000 male participants into 4 treatment groups: active aspirin and active beta-carotene, active aspirin and placebo beta-carotene, placebo aspirin and active beta-carotene, and 2 placebos. The designers of the study are testing the hypothesis that if the drugs are effective, the active treatment groups will experience 20% lower mortality from vascular disease and 30% lower mortality from cancer. But we know that different people react differently to drugs. Perhaps this difference would be reversed in a second trial with different participants. How confident can we be that these treatments are genuinely effective? Well, in this program, we're going to find out, because formal statistical inference enables us to quantify our confidence in the accuracy of random surveys and randomized experiments, to verify impression by calculation. What we're going to do is make some probability calculations. Let's use a simplified version of the Gallup survey. We'll assume that Gallup drew a simple random sample of 1,500 Americans and discovered that 45% were afraid to go out at night because of crime. Now, our sample proportion is 45%. It's an estimate of the unknown proportion of the entire population of Americans who stay home at night for fear of crime. But how accurate is our sample proportion? How close to the truth is it? Well, in order to find that out, we have to calculate the sampling distribution. Well, if the sample size is relatively large, like in our poll, then the sampling distribution is almost certain to be a normal curve. The mean of the curve will be the true proportion of people afraid to go out. And the standard deviation can be calculated this way, where P is the true proportion and N is the sample size. What this means is that if we repeated the sampling many times, if we did indeed send out waves of interviewers across the nation, every time we get a value of a sample proportion somewhere on this curve, the values would vary according to this distribution. That's why it's called the sampling distribution. The value of the standard deviation will determine how tight our normal curve is, and so how often our sample proportion will be close to the actual proportion in the total population. So let's calculate the standard deviation for our example. Well, you can see right away that we've got a small problem. We don't have a value for p, the true proportion of the population. In fact, if we did, we wouldn't be going through this whole thing in the first place. But you can see from the equation that if n is relatively large, as it is at 1500, then in fact an exact value for p isn't critical. The sample proportion is close enough. Let me explain that a little more. Because n is the denominator of a fraction for which we want the square root, if n is large, the fraction is small, and the square root doesn't change much. Furthermore, the numerator is p times 100 minus p, so the product also limits the variation. If p is 40%, then 100 minus p equals 60%, and 40 times 60 is 2400. But if p is 50, 100 minus p equals 50, and the product is 2500, pretty close. It's only when we're unsure whether p is, say, 20 versus 50, that the numerator changes more drastically. If we conduct a proper random survey, we should be able to estimate p more closely than that. Okay, now let's calculate the Gallup poll result. We have n equal to 1500, and for p, we use the estimate based on our survey, 45%. The result is 1.29. We call this the standard error of estimate. Now we can put the numbers, the mean and standard error, onto our normal curve, and by the 68, 95, 99.7 rule we've already learned, we know there's a probability of 95% that the true p will fall within 2 standard deviations of the sample proportion, 2 times 1.29, or within about 2.6% of the true proportion. To state it formally, the probability is 0.95 that the sample proportion will fall within plus or minus 2.6% of the unknown true value of people in the total population afraid to go out at night because of crime. In statistical shorthand, we can now say we are 95% confident that the true proportion lies in the interval 45% plus or minus 2.6%. We know the probability of our method giving a correct result. This confidence statement asserts how confident we can be that a specific application of our method is correct. Okay, now we can combine the calculations we've done into a single formula. If a simple random sample of size n is drawn, and n is large, a 95% confidence interval for a population proportion p, say the true proportion of people afraid to go out at night, looks like this. I've introduced a precise notation. P is the true population proportion, while p hat is the estimated proportion we obtained from a sample. Both p and p hat are measured in percent. Let's look at this more graphically. Here's our normal curve for the population, with the true mean p as indicated. Now suppose that we take many samples of this population and compute the mean proportion for each sample. Here's one with its 95% confidence interval shown. As you see, the confidence interval around the sample mean includes the true mean p. Here's another hit, another. Whoops, there's a miss. Its confidence interval doesn't overlap p. Now some more hits, and so on. What we're saying is that 95% of our sample proportions will be hits. Only 5% miss the true proportion. We're now in a position to read our newspapers much more carefully. Reliable public opinion surveys, like Gallup and Lou Harris, and the Bureau of Labor Statistics Unemployment Survey, always announce confidence intervals to help us interpret our results. But alas, editors often cut these out. Here's the story on our Gallup poll of people afraid to go out at night. Using calculations such as we've just done, Gallup arrives at a confidence interval for its weekly surveys of plus or minus 3 percentage points. So when we read that Gallup asked 1,555 Americans if they were afraid to go out at night because of crime, and 45% said yes, we can be 95% confident that if all adult Americans had been asked, between 42 and 48% would have said yes. The Bureau of Labor Statistics chooses to announce its unemployment survey results at a 90% level of confidence. The Bureau states that based on a monthly survey of 60,000 people, the proportion unemployed is within plus or minus 0.2% of the figure they'd get if they counted everyone. So when the headlines announce 7.9% unemployment, the BLS is saying with 90% confidence that between 7.7 and 8.1% of the labor force is out of work. Statistics allows us to make inferences about a population on the basis of a sample. And as we've seen, the larger the sample size n, the more confident we can be that our inference is close to the truth. Now, the square root of n that appears in our calculations shows that to reduce our margin of error in half, we need a sample size 4 times bigger. That's why the Bureau of Labor Statistics goes to the trouble to interview 60,000 as compared to Gallup's 1,500. A Gallup poll can afford to be 3% off. The unemployment rate can't be. Too much economically and politically is riding on it. But confidence isn't free, remember. It's directly related to sample size. The Bureau of Labor Statistics could choose to announce its findings with 95% confidence. But if the sample size remained at 60,000, then the interval would be larger than 0.2%. Now we're in a position to see how statistical inference is actually used in making things, in judging the quality and the reliability of an industrial process. At its Oklahoma City works, AT&T manufactures computerized electronic switches that connect your telephone to the telephone of the person you're calling. These switches are largely made up of complex electronic elements called circuit packs. Connie Moore is in charge of quality engineering here at the plant. She told me a little bit about the basic ingredients of quality control as practiced at AT&T.
A process capability study is an industrial investigation that uses mathematical techniques to gain information about a process and, at the same time, take steps to improve the operation. Here's how it works. The results of a process are plotted on a control chart such as this. In a process capability study, we concentrate on what are called out-of-control conditions and find the assignable cause and set out to eliminate it. As an example, this out-of-control condition might have been caused because a new operator produced too many defects because she didn't know how to do the job right. Elimination of the assignable cause is accomplished by training the operators. This out-of-control condition might have been caused because a machine was set up incorrectly. In order to fix this problem, we fix the machine. Once all assignable causes are eliminated, the process is driven to its process capability. As you can see, the defect level is much lower and the variability less. This is what we call a stable process.
To see a specific example of what Connie's been talking about, let's look at an application of distributions, standard deviation, and confidence intervals right here in the plant, the wave soldering machine. Bill Bennett's in charge of this area. Bill, can you tell us how the wave soldering machine works?
Sure. This wave soldering machine is used to mass solder through-hole mounted devices to the printed wiring board. Wave soldering is a delicate process which mechanically bonds these leads to the printed wiring board by flowing molten solder over the leads and the printed wiring board simultaneously. In high-density circuit pack manufacturing, we're talking generally 2,000 leads per circuit pack, it's more advantageous to solder all these at once instead of using the traditional method of an operator and a soldering iron and hitting each joint at once. The wave itself is a specially designed nozzle which flows the solder up at such a designed velocity and angle that we have almost perfectly soldered board at the end of the machine.
Mary Lou is process checker of the wave solder machine. It is her job to both monitor machine parameters such as wave height, temperature, conveyor speed, and also to evaluate product quality. In order to evaluate product quality, Mary Lou takes a sample of product each hour and checks it carefully for possible defects. Once Mary Lou has completed her sample and evaluated the quality level, she plots a point on the control chart. If the point is near the center line, that indicates that the process is operating as expected and the machine goes on. However, if the point is plotted outside the control limit, that indicates that unnatural variation exists in the process and immediate action must take place. If we looked at 100% of the product, it would take more time, more people, and would not give us any better information about the process. Therefore, statistical sampling techniques give us an economic and accurate way of measuring process quality.
First, a quick review. Bad soldering would produce bad connections, both in the circuit pack and in your telephone conversation. So AT&T wants to monitor the performance of the wave soldering machine constantly and to take action if something goes wrong. To accomplish this, process checkers like Mary Lou take a sample of 5 circuit packs every hour. They inspect these packs carefully and calculate a number that expresses the quality of the soldering for each pack. That number is recorded on a process control chart. Now, any industrial process has some variability. When the soldering machine is doing its job properly, the quality index will vary according to a normal distribution. Now, let's say that we know from long experience that the mean of this distribution should be 100 and the standard deviation 4. These numbers are hypothetical, by the way, but they give the idea. Anyway, in our example, almost all quality index values will fall within 3 standard deviations, or 12 points, either side of the mean. That is between 88 and 112. This is the range AT&T accepts as excellent soldering quality, as long as it's centered around a mean of 100. But if something goes wrong, if the conveyor moves at the wrong speed, or if the temperature's too high, or the solder doesn't flow properly, the mean of the distribution may drop below 100, and quality will deteriorate. AT&T uses the data from the hourly samples of 5 circuit packs to decide if the mean of the process is maintaining an acceptable value, and to take action if it's not. Imagine one sample has a mean quality index of 98.17 for the 5 circuit packs. Another sample has a mean of 94.22. Should AT&T adjust the process in either case? Guess what? We come right back to the square root of n. We know, after all, that the sample mean has a standard deviation smaller than that of individual measurements by the square root of the number of packs in the sample. So the distribution of the sample mean has a standard deviation of 1.79. If the mean for all the circuit packs produced stays at 100, then the sample mean will have a normal distribution, also with a mean of 100, and with a standard deviation of 1.79. So 97.5% of all samples will have a mean higher than 96.42, which is 2 standard deviations below the mean. If 1 hour's sample has a smaller mean, there's only a 2.5% chance that this is due simply to normal variation. In other words, a sample mean below 96.42 is a signal that something in the wave soldering process has probably gone wrong. Combining this calculation with a graph that plots the behavior of the process over time gives us this kind of control chart. It tracks the sample means against time, 1 for each hour. The center line at 100 shows the target value for the process. The line here at 96.42, called the control limit, shows when action is needed. Control charts combine formal statistical inference with graphical display of data in a way that can be used by someone without statistical training. Each of the many processes that are part of manufacturing a circuit pack is monitored by a control chart, more or less like these. If all of the processes are kept on target, almost all of the circuit packs will work properly when they're completed and tested. That not only keeps the quality of the final product up, but also keeps costs down by catching malfunctions quickly, eliminating the need to repair or scrap faulty parts at the end of the assembly line. Let's see how a control chart works by looking at data in a case where something has gone wrong. With the help of a computer, I've simulated sample means for 20 consecutive samples of 5 circuit packs. The control chart makes it clear that the sample means in later samples are systematically less than those in the early samples. Not only are means for samples 12, 15, 16, and 20 outside the control limits, but the last 11 means are all below the center line. Something is amiss in the wave soldering machine. In the long run, you remember, only half the sample means will be below that line if the process mean is truly 100. It appears that the process quality shifted downward at about sample 9 or 10. In practice, the so-called out-of-control point at sample 12 would trigger an investigation that should find and correct the cause of this trend. And that's how sampling and statistical analysis help keep the wave soldering process on track. Quality control is an important ingredient in maintaining the reliability of almost every manufacturing operation. In all of our examples, I've quantified the trustworthiness of the statistical statements by giving first the result, then a degree of confidence. So an unemployment rate of 7.9% means that between 7.7 and 8.1% of the labor force is out of work. And we got that result by a method that's correct 90% of the time. Again, the Physician's Health Study is investigating whether a daily dose of aspirin leads to a 20% reduction in cardiovascular fatalities. The PHS is using such a large sample, 22,000 doctors, because it wants to have 95% confidence in its results. If you want higher confidence, say 99%, or a 1% chance of a false statement, then you can collect the data in order to provide it. But remember the ubiquitous square root of n. The larger sample size necessary for higher confidence in a survey or an experiment can be very expensive. What you cannot demand is 100% confidence. But even with meticulous methodology and accurate arithmetic, you always have to evaluate the complete context in analyzing any findings. In fact, one very important goal of the statistician is to identify all of the possible variables that might affect and thereby confuse a conclusion. Statistical methods attempt to control for those variables. And as we've already seen, an experiment is the best way to do this. But there's some situations in which an experiment just isn't possible, and in which seemingly clear conclusions can be very misleading. The example I'll give is hypothetical, but it's based on a study of admissions to graduate programs at the University of California at Berkeley. We'll call our hypothetical campus Metro University. Recently, there was a demonstration at Metro about discrimination against women, based on some pretty dramatic statistical evidence. 80 men applied to limited enrollment courses at Metro last year, and 35 were admitted. That's almost half. 60 women applied, but only 20 were accepted. That's just 1/3. Could this be an accident? Probability tells us that the difference between male and female admissions here is so large that it's very unlikely to arise simply by chance. So it certainly seems like a clear-cut case of discrimination. What other explanation is there? Why should the percentage of men accepted in limited enrollment courses be so much higher than the percentage of women? Metro is concerned. It's proud of its progressive record on women's equity. So analysts took another look at the data, and this is what they found. Men and women tended to apply to different departments. The organic chemistry course is very rigorous. 40 women applied, but only 10 got in. That's 1/4. 20 men applied, and only 5 were admitted. Again, 1/4. So there doesn't seem to be any discrimination here. The only other limited course offered at Metro is the history and sociology of the TV sitcom. Now, frankly, this is known as something of a soft option compared to organic chemistry. Anyway, 60 men applied, and 30 were given places, while 10 of the 20 women applicants were accepted. That's 50% of both groups. Again, no apparent discrimination. Yet when only the totals are considered, as we saw at the beginning, almost 44% of male applicants got in, as compared to 33% of females. But that's because 2/3 of the women applied to the tougher course, whereas 3/4 of the men wanted into the easier sitcom class. So the conclusion to draw from a case like this is that it's important to examine the data in detail appropriate to the question we're asking. There's an important real-world lesson here about understanding statistical methods. Almost no one who hasn't seen an example like this can believe that equality in each of several cases can, when lumped together, result in so strong an appearance of inequality. At a time when statistical evidence of all kinds is increasingly being used to formulate social policy and resolve legal disputes, it is obviously crucial that we select, analyze, and interpret our data with great care. So, if we follow our procedures precisely and calculate our results correctly, then we're home free, right? Wrong. There's always some chance, some probability, however small, that the luck of the draw in a random selection will lead to an error or to a case that we've already ruled out because it's just too unlikely. That's why statistical evidence isn't proof. But then again, most kinds of evidence aren't proof. At least statistics announces its degree of trustworthiness openly, right down to the margin of error.